Hi, everybody. So we'll continue with 2.5. As I mentioned, now we did the introduction to calculus, and right. So in 2.4, we introduced the limits, the definition, and the tangent. Right, by starting by the tangent, and we did some examples, and now we have a good idea about some techniques to use with the limits and their laws, right? And we also used the limit at infinity, and we did kind of a technique to resolve the issue, and we understand now that the one-sided limit and idea, we talked about it but not formalize it. So now in 2.5, let's formalize these others idea of the limits. So one-sided limits and the continuity, which are going to be important topics here. Yeah, so we're moving on in calculus now, and that's it. So what is one-sided limit? So as when I did some examples, right, I talked about, so to make it simple here, let's say this is the curve, and you're interested in this point here. So if you're approaching this point from the left side, let's say this is 1. So you're approaching this point from the numbers that are less than 1. We say 1 kind of negative this way, but not meaning a negative 1 or something. We just mean approach 1 from left, right? So it's going to be this way. So if you see that, that's what it means. Which means now if somebody says, what does this mean? Okay, it's clear. You're approaching 1 from the numbers that are greater than 1, which means these other side, right? Okay, and of course you trace the function as you do that. So here is an example. We have a piecewise function. It has 2 rules. If x is less than 0, it behaves this way. And if x is greater than or equal to 0, it behaves this way. So let's look at what happens to x, the limit, as x approaches 0. Well, you can't tell because that's 2 different rules and it disconnects here. So let's look from the left side. What happens? Well, from the left side means you're going to be, if you project it here, means you're going to be using this function and going towards that point as x goes to 0. This point is going to keep going towards -1. And if you do the limit of x from the right side, the right side x going this way. So if you project over the function as you keep going, here it's going towards 1. So it's not going to the same limit from the right and the left, right? So this is what's kind of explained here. And this is what explained as well in this one. So these we call the one-sided limit. And we're going to say also the right hand limit, and this one the left hand limit. That's another way to say. All right, and they are different. So now we're going to present something. The right hand limit is just as I described it in the example. It's 1. Here we call it L in general. the left-hand limit is the example -1, and here it's m, some number in general. So when do we say the limit exists? The limit exists if and only if the right-hand limit and the left-hand limit are equal. All right. So in this case, so going back, all right. These limits, so conclusion, right? Based on definition, the limit as x approaches 0 of x does not exist, all right? Does not exist. Why? Because the right-hand limit and the left-hand limit are not equal. And we're using theorem 3. So I called it definition, which is theorem 3. So if we want to be consistent with the numbering. All right, so more examples. Let's investigate the limit of f of x as x approaches 0. So we need to do the left hand limit, which means x less than or equal 0. So we're going to use this for approaching 0, you know, the left side one. So that's the formula you will use, right? Negative x. Then for the right hand limit, x greater than 0, you're going to use this. And you see square root of x, that's the part we use. Then we find that they are equal. Since they are equal, then the limit exists as x approaches 0, and it's going to be 0. The limit equal to 0 does not mean does not exist, right? So, and I've seen that before, and I've seen it also this year, where someone would say, yeah, it approaches 0 from both sides, so the limit does not exist. No, it exists, it's equal to 0. And here is a graph to show what that means. So it's coming from this way, and it's going to 0, and it's coming this way, and it's going to 0, right? Does not exist means, for example, it's going this way, it's going to 0, but this one going, let's say, to this number or something else, right? So this is the, and this is 0. Here is an example for does not exist. A similar example we did in 2.4. From the left is -1. And from the right is 1. They are different, so it does not exist as x approaching 0. So let's not confuse the one-sided limit with the whole limit. The one-sided limit exists, it's -1. The right-sided limit exists, it's 1. But the limit as wholly kind of approaching 0 does not exist. And that gives us a really good, precise idea about the graph and the function. All right, the continuity. Three cases where the function is not continuous. If there is a hole in the graph, right? If there is a jump in the graph, and if there is asymptote, vertical asymptote, for example. Some call it infinity. So Hij, if you use it this way, which is easy to remember. The whole infinity means a vertical asymptote going towards positive or negative infinity, and J, there is a jump. So why it's important to know the continuity? Because if there are problems of the limit there, and also which means there is a problem with the derivative later, which we will see. All right. So what is the limit? And we will talk about this example here, if there is a hole and if there is a jump on infinity. So we already did this one, this one. I need maybe later emphasize a little more this one. All right, so that's pretty much the example there. So maybe I need to give you some other, whether it's defined or not defined, there is a hole there, so that's a problem. That's a jump. And let's say for example this way, that's infinity. All right. So the continuity of a function Rn number A. So now 3 cases and 3 conditions for it to be continuous. If so, we say it is continuous if it satisfies 3 conditions. F of A is defined. The limit of f of x exists. So you see now you connected with the previous talk of the limit. And 3, look, this is the important one. Limit of f of x equal f of a, right? Because it may not necessarily be. So let's go back to this example. If this is 1, this is 2, and this is 3. This is important to understand what we did. What is the limit of this function f of x as x approaches 1? Right? Is it going to be the value of x3? You see? So f of 1 is 3, because there is a hole here, it's not a 2. The value of 1 for this function is 3. Well, we go back to the idea of the limit. If we do the limit from the left, we trace it as we go this way, it's a 2. And if you do the limit going this way, it's a 2. So the value is 2. However, 2 is not same as f of 1. So it's possible for the limit, of course, to exist, but not equal to what's expected for the function value at that point. So f of 1 is 3. However, the limit is 2. Does the limit exist? Yet, but it's not continuous. So that's where we know it's not continuous. That's number 3. This important condition here. If the limit and f of a are not equal, then that doesn't satisfy the third component for the continuity to be existing there. All right. All right, so if f is not continuous at x equal a, then it is continuous at is discontinuous at x equal a. And of course, we say if it's continuous at some interval a, b, if it is continuous at every point over the interval. So there is no jump, no hole, no infinity, and so forth. So we start with looking at a point, then if every other point meets in some interval, then it is continuous over that. So you see, like, this function is continuous over A to B interval because it's continuous at every point on that interval. All right, so examples. Of course, you need to know where the function is not continuous at. This is a line, it's continuous at everywhere because the domain here is negative infinity to infinity. X cannot be 2. If it's 2, it becomes undefined, right? So we're going to look at these graphs in the next slide for these. This one, when X is not 2, does not equal to 2, it takes this rule, this line, y equal x plus 2. When x equal 2, it takes this value of 1. We've seen these before, so let's just look at the graphs and investigate. All right, so as you see, no problem. As you see, there is a hole in the graph at there, all right? As you see in this one, there is a hole in the graph, but there is, it's defined at this point. And for D, we've seen similar, and this one, another one, similar behavior where it behaves one way in this side and one way in this other side. For these sides, we call them subdomains. So this is a domain and this is a domain. So for example, in this subdomain, which is X, I'll show it to you here, which is X is greater than 0, it's 1 over X. That's a subdomain. And this function takes 1 over X form there. And this is a subdomain, right? And here it is, X less than or equal to 0. All right, so the function A is continuous everywhere because 3 conditions are met. Is not defined because it is continuous everywhere else, right? So this one, there is a hole there, so it's discontinuous there, right? Just the way we described it. Now this is the important one because the others are kind of direct. It is discontinuous. Why? Because the third condition that I mentioned is violated. The limit exists. So if we look at this and somebody asks you what is the limit of h of x as x approaching 1, 2, 3, 4, as x approaching 2, well, you're going to do left and right and you're going to find out it's 4. But if what is h of 2? Is it 4? No, it's 1. So the third condition is not met. The third condition that I stressed on is not satisfied. If that's not satisfied, then it is discontinuous, right? So that's the hard one sometimes to see, but the others are not, they are okay. The function f is continuous everywhere except at x equals 0. It fails to exist. Of course, this breaks this. Here the limit does not exist, you see, because we know that already, because from the left and right is not the same, right? And here, since does not exist, x approaches 0, we conclude then g fails to be continuous, you know, similarly. So keep in mind the 3 conditions for it to be continuous. And this is nice example with different graphs. If the limit does not exist and it breaks that, that's becomes kind of easy to figure out. If f of a has to be defined, if it's not defined there at all, then it's not, like that example. And of course, this one where the limit exists, however, it's not same as the expected value. All right, so the properties of continuous functions. This in general kind of to know as a common knowledge thing. The constant function is continuous everywhere. You know, if you graph a straight line, horizontal is continuous everywhere. The identity function is continuous everywhere. So if you graph this y equal x, it's continuous everywhere. F of x power n, where n is a real number, they're continuous. X power n, for example, continuous everywhere. X squared. F plus g is continuous. If these, then f plus g is continuous at x equal a. F times g is continuous, and of course this one where it should not be 0. Those are not something to worry about, but to understand the continuity and its 3 conditions, that's the most important. Polynomials are continuous. Rational functions is continuous everywhere except, you know, where, of course, the denominator is 0. So one thing to keep in mind, we are interested in the continuity, right? Continuous here, for example, f of x equal 1 over x plus 1. So it's continuous everywhere except this at -1 because it makes the denominator 0. But if we're not talking at this point, it's continuous everywhere else, right? So that's what we need to keep in mind. If we are interested, let's say, if we are interested now, what about x equal 2? You know, that a now is 2. Well, it's continuous there, right? So that's what we need to keep in mind. You know, some examples, polynomial, continuous everywhere. Watch for this. This cannot be equal to 0. So that's how you investigate. Can this equal to 0? No, because x squared cannot be negative. This is supposed to be I and negative I, which is not real intercepts, right? So no, so it's continuous. Now for this one to investigate whether yes or no, we need to solve. So once you factor it, you'll find that it's going to be discontinuous at these 2 values. So some algebra comes to merge in here. Another topic, but not a big deal, but it helps understand different things. It's intermediate value theorem. And one way to think about this theorem is if you have a different, I think one way I'll introduce it kind of my way, then we talk about it. If you have 2 different values and you multiply them and you get a negative sign. So let's say, let's give you a picture first. Yeah, then we talk about this one. Let's say f of a, f of b, and a and b. So look what happens if you do f of a times f of b. This is negative, this is positive. Whatever numbers are, negative times positive is negative. So if you multiply f of a times of b, you get a negative number, which is less than 0. It means there is an x-intercept. There is a 0 in AB, in this interval, right? So that's what this kind of intermediate value theorem, if you investigate an interval, and we can close it for now on this one. If there is an interval and you investigate A and B and you find out that they have opposite signs, then the graph must be crossing the x-axis, so there is a 0. So if f is continuous on AB, in any number f of A and AB, then there is at least one number C, such that f of C equal m. So here, before we get to that, you just hear another general thing. If you have A and B, and of course there are A and B here, right? So if there is a number between this f of B, then there must be it must cross the graph. That's what this all means. And you get a C between A and B, right? And it could happen multiple times. So you see this function, you take m and it crosses, so you may have more than one. But here it says that there is at least one. It's gonna happen. So the next theorem is an immediate consequence of the intermediate. If not, it tells us about the 0. That's the one I explained, the 0 of this. Because why we're able to say this? Because for continuous functions, we can't say this unless the function is continuous, because it could jump, right? If it jumps, then it won't apply. That's why the intermediate value theorem uses this idea here of if a function is continuous, which means it doesn't break, it doesn't jump, then this is going to happen. All right. You see, f of A, f of B, if there is a jump or something, then we don't apply it. So show that f, example, show that f is continuous for all f values. Well, it's polynomial, so it's continuous. Compute f of -1 and f of 1. So we're testing an interval here, f of -1 and 1. And based on the results, do you think, deduce that there must be at least one number C such that this is going to happen? All right, it's a polynomial, the degree, so it is continuous. F of -1 gives us -1, f of 1 gives us 3. Yeah, so if you do -1 times 3, it is negative, it is less than 0. So yes, based on theorem 5, it tells us that there must be at least one number, x equals c, with such that f of c equals 0. So there must be a 0 there for this function between -1 and 1. All right. So, and that's, when I did the open things, so now maybe we can go back and put them back that we talked about it for that. We can say that there is a 0 in AB because we're not including them in that point to be one of them. It's just, it's in between. All right. So it's an easy, nice theorem to investigate whether you have a 0 or x-intercept in an interval, not for a continuous function. And of course, we can locate, there are methods to solve. If it's not easy to solve, we can set a program or trace a function and find it. So we can locate the root. The root is also the 0. It's also the x-intercept. We go to that midpoint and investigate, and we find out, we narrow it until we find out a little more where the interval is, right? and we can investigate a little more. So if we take these interval again, we go to the midpoint, we find it's this, and we investigate that midpoint, f of this with this midpoint, f of this with this midpoint. It's an elimination process, right? You investigate these two ends, which means you're investigating this side, or you're investigating this one with this one, so which means you're investigating this to find out if the root is here or here, right? So now we, after we do that, where the signs are different, we find it's between this and this. So we can keep doing that until we get to it. So, all right. So from this table, this kind of computational investigation, we find that the root or the zero is approximately 0.68, right? So, you know, somebody will say, well, you know, what's going on? Keep in mind that you need to find different signs each time to accept the root. So let's, you see here, f of 0 is -1, f of 1 is 1. So you take this -1 and 1, you multiply them, which means two different signs, right? They have to be less than 0, which means the answer is negative. In that case, you say yes, between -1 and 1, it's crossing it. If their y values or f values are opposite signs, then yes. Then the investigation now, this is too big. We go to the middle and we investigate now this with this and this with this. Again, just like we did here. So that's what happened. 0.5. If you try 0.5, you get negative value. All right, you get negative value. For 0, it's -1. For 1, it's 1. Since we found negative value, then we're going to use, you see, f of 0 is negative, f of 1 is positive. So we want 1 to be negative, 1 is positive. So since this is negative, we need the other side of the interval to give us the positive, okay? So you want 1 to be negative and 1 positive. Then we get this interval, 0.5 and 1. Its average is 0.75. We plug in 0.75, we get positive. So now this is positive. We want the other end that has a negative. All right, so now it's this interval and so forth. And, you know, we do kind of investigation until we find where the 0 is, where the root is. And you see, this method is done when it's not easy to figure out the roots or the zeros, like we did for quadratic function. You know, for quadratic function, x squared plus 5x plus 6 equals 0. You can use quadratic formula, or you can use factoring. So if you do, so if you try, so -3, -2, so these are the roots. So what does all this mean? If this function, for example, we don't know how to solve for this, and we're investigating, we may be taking, so what you can do, for example, take this here, -2.5 and -1. Plug them in, you should see that, you know, they have opposite things, signs. That tells you there is a root in between. So you can average them, you get a point, and you can try until you get close to -2. So just to show you that investigation, when it's done, when there is no way to solve, the computer or that graphing calculator, this is the technique we're talking about, that it's going to be doing itself. All right, so the process of finding the root of f of x used in example is called the method of bisection. All right, so please remember this one. It is crude but effective, and it can be coded in those machines, and you'd be able to find the roots of functions that there is no method, for example, to solve, or right. Thank you.